In the 1960s, U.S. Air Force Colonel John Boyd watched fighter pilots die because they could not process information fast enough. Survival in air combat meant outthinking opponents in fractions of a second. From those observations, Boyd developed the most influential decision-making model in modern military history, the OODA loop: observe, orient, decide, act. Looking at this standard flowchart, you see the loop presented as a simple checklist: see something, understand it, pick a response, execute. This interpretation treats the cycle as a speed contest. The side that cycles faster than the enemy wins. But look at Boyd's actual system design. It rejects the linear model. Orient sits as a massive center box. Boyd called orientation the Schwerpunkt, the center of gravity. Observe, decide, and act are small peripheral nodes feeding into it. Notice the dashed lines radiating outward from orient. Boyd labeled this implicit guidance and control. This is the mechanism where a human's prior experience, cultural context, and moral intuition filter all incoming data. Your orientation dictates what you even notice during observation and restricts the options you consider during decision. Orientation is a contextual and moral act. Attempting to accelerate this specific phase with algorithms introduces a structural risk to the decision cycle's integrity. The U.S. defense establishment is now mandating the integration of artificial intelligence and large language models, or LLMs, into command and control architectures. An LLM is a complex algorithm trained on vast text datasets to recognize patterns and generate plausible outputs. The objective is to match the extreme tempo of modern warfare. The prevailing assumption is that dropping an algorithm into the OODA loop simply accelerates each existing phase, making the entire cycle faster without altering its nature. This diagram maps the OODA loop after AI integration. The system splits vertically down the middle, creating a structural asymmetry. On the left is the machine speed zone. On the right, the human speed zone. On the machine side, the phases stack vertically. Observation, analytical orientation, and option generation all occur in rapid succession. High-speed data flows downward through these nodes in milliseconds. This temporal distortion forces a critical question. What happens when a machine dictates the operational tempo to a human operator, who is legally and cognitively required to move slower? This chart assesses AI insertion points across the OODA loop by risk. The green bar at the top represents the observe phase. Here, confidence in AI is high. In real-world deployments, the military uses Maven's Broad Area Surveillance and Targeting System, or BAST, which uses computer vision to detect equipment in satellite imagery. Another system, the Army Intelligence Data Platform, or AIDP, parses and visualizes thousands of battlefield messages. These systems flag anomalies and correlate signals. They change the scale of data ingestion without requiring moral or contextual judgment. Automating observation allows the military to handle data volumes that would otherwise paralyze a human staff. This operational efficiency creates a precedent for integrating AI into the more sensitive cognitive phases. The danger emerges when AI enters the orient phase. An intelligence analyst might prompt a model to infer the presence of an armor attack battalion based entirely on equipment signatures and spatial patterns. Warfare operates as a complex adaptive system. This is an environment defined by novelty, emergence, and deception, where adversaries actively try to subvert your mental models. Cause and effect in a complex system resist algorithmic prediction. Large language models are built on historical pattern matching, generating outputs statistically consistent with their training data. They can tell an operator what past situations looked like, but they lack the strategic comprehension to understand what a novel, deceptive situation actually is. Returning to the split-screen model, look at the coral bracket connecting observation and analytical orientation. When an AI detects a pattern and immediately delivers an interpretation, those two distinct phases fuse together. The phases collapse. Watch the output arrow. It bypasses the human orientation box and skips straight toward the decide phase. The operator receives a pre-packaged meaning instead of the raw materials necessary to build their own mental model. When the machine packages detection and interpretation together, the human outsources the cognitive work of orientation to an algorithm that cannot actually understand the battle space. Moving to the decide phase, AI expands the option space. -3 is an Air Force battle management experiment testing AI-human coordination. In these tests, AI-generated courses of action achieve 97% tactical viability, outperforming human planners. But this creates a structural bottleneck. The machine delivers ranked targeting options in milliseconds, slamming into a human authorization gate that requires minutes of genuine deliberation. This extreme time compression triggers automation bias. Automation bias is the psychological tendency for human operators to defer to algorithmic recommendations, a risk that spikes under high stress and cognitive load. The International Committee of the Red Cross, or ICRC, warns that under these conditions, operators routinely miss anomalies and follow faulty AI suggestions. Declining the prompt feels like second-guessing a superior analyst. When the operational tempo demands humans match machine speeds, formal oversight degrades into a rubber stamp. The human is left holding the legal liability but exercises no functional authority. The solution is not to slow down data ingestion. The volume of modern battlefield data and the tempo of adversarial operations make AI assistance a requirement. Instead, the solution requires a new systemic architecture. This diagram proposes an orientation checkpoint. The high-speed AI pipeline pushes data into a large dashed orange box, forcing a structural pause. Inside the checkpoint, the operator must engage with specific prompts. The first card asks for assumptions, requiring the operator to identify what specific evidence would disprove the AI's assessment. The second card addresses missing context, articulating political sensitivities and ethical boundaries invisible to the LLM. The third card forces a metacognitive check, orienting or endorsing. The operator must ask if they are actively building an independent picture of reality or just agreeing with a fast, confident machine. This checkpoint operates at human speed, measured in minutes, not milliseconds. That friction is a feature. It preserves the cognitive rigor necessary to win wars. Colonel John Boyd did not build the OODA loop to describe how machines process data. He built it to map how human beings think and adapt under extreme adversarial pressure. If defense systems are designed to deliver finished intelligence rather than raw analytical building blocks, the critical orient phase is bypassed before a human ever touches it. Keeping a human in the loop means nothing if the speed of the architecture turns their role into a ceremonial loophole. The OODA loop remains a model of human competitive cognition. The goal of defense technology must be to augment that cognition, not replace it. The fastest loop is not the best loop. The best loop is the one where someone is actually thinking.